University.
This week on Office Hours. Harry Potter and numerous sci-fi movies have popularized the idea of a cloak of invisibility, but Duke engineering professor David R. Smith and his colleagues developed a prototype version of the real thing. To create the cloaking effect, Smith engineers composite materials called metamaterials. In 2006, Smith's research on invisibility was selected as one of the top 10 scientific breakthroughs of the year by Science magazine, and he was named one of Scientific American's top 50 researchers. Professor Smith joins us today to take your questions on the science of invisibility.
Greetings. Thanks for joining us on Office Hours. My name is Karl Bates. I'm the research editor in the Duke News office. We're joined today by David R. Smith from the Department of Engineering. It sounds like the stuff of science fiction or fantasy, a material that can somehow make a solid object magically disappear. But it's not magic. It's state-of-the-art physics and a little bit of electrical engineering. It's a technology called metamaterials. Our guest today is David R. Smith. He's the William Bevan Professor of Electrical and Computer Engineering. He's also the director of the Center for Metamaterials and Integrated Plasmonics. Dr. Smith's work has twice appeared on the cover of Physics Today and twice been selected one of the top 10 breakthroughs of the year by Science magazine. He is also one of the most highly cited physicists of the last decade, which is to say that metamaterials are a very, very hot topic. So, let's start at the very beginning. Tell us, please, what metamaterials are.
Metamaterials are artificial materials. You can think of a material as being made of atoms and molecules. That's our normal thought. You know, this table is made of wood, which is ultimately made of a bunch of atoms put together in a certain way, and that's what gives the table its properties. A piece of glass, a piece of plastic, the same thing. So a metamaterial is just that concept, but you don't have to start with atoms. You can start with other objects. And what really makes something a homogeneous material is the wavelength. And I'll use light as an example.
Okay.
Light can be described by having a wavelength. If that wavelength is bigger than any particle that it's passing through, if it's going through a bunch of little objects and the wavelength is larger, all of those objects sort of average out and it sees like a continuous material. Mm-hmm. And so a metamaterial is our attempt to duplicate nature and create types of materials and hopefully get something that nature didn't think of.
Okay. And physically, what are they made out of?
Physically, they can be made out of anything. It's a very broad, basic concept. In our group, what we've done a lot of is use circuit board techniques, and I actually have a sample here that I brought over.
Mm-hmm. We have a still photo for people to see.
This is just basically circuit board, so it's a little bit of polymer or plastic on which is copper, metal. It doesn't have to be copper. And you take the copper and you shape it into different shapes. And again, we're talking about microwaves, which are part of the electromagnetic spectrum. The wavelength of microwaves that we use is about like this, a few centimeters, a couple inches. And if you look at the little patterns here, these little objects are on the order of millimeters. So this, even though it looks like a big, hollow, empty, weird thing to us, actually looks like a continuous material with unusual properties to the microwaves that pass through it.
These copper features they look like little squares, and they're repeated over and over and over again on each slat of the lattice in a very repetitive fashion.
That's right.
You also have a circular piece. You have a couple different arrays that you've tried getting at different regimes of radiation, but you started with microwave. And
right.
We'll come back to why that is. So how does this work? What does a metamaterial do? What is this repeating series of printed copper doodads? They look like little icons. What's the magic here? How do they work?
Or hieroglyphics. It's basically if you have a book, and the book is composed of a bunch of words, the words are composed of letters, and the letters, when combined together, tell you something, begin to have meaning.
Okay.
So that's kind of like what these are. They're little letters, and when you combine them together, they form an object, and electromagnetic waves understand this object. They react in a certain way with the object. So these little doodads, these little patterns, are meant to control either the electric or the magnetic properties of material, of a wave. You combine both, and if you can get full control, you can make a wave do whatever you want it to.
So in the early examples, when you first published in 2006, you had an incident wave of microwave coming into this lattice, and you were able to basically part the thing and bring it back together on the other side such that it passed around a solid object, and on the far side an observer wouldn't know, except that the signal got weaker, wouldn't know. We actually have a video that shows what that
So I just
like.
want to mention this is
Sure,
not
yeah.
this sample. It's one of these curved samples, but that's
Right,
right.
it was
It's,
the
it's a
curved
type
one.
of
Yep.
material.
Okay,
Yes.
let's look at the microwave video if we could, and you can talk us through it.
So what you see here in the beginning is this is just a wave passing through space, what it might look like. And the red and the blue are like the crests and the troughs of the wave.
Okay.
And so it's
Moving
traveling
from left to right.
because that's what waves do, they travel. If you put something in its path, it scatters. So it hits something and it does warps everything because you've got your incident wave shown here hitting an object and then scattering. Now if you put this cloak around it, what it does is it tries to restore what was originally the plane wave. So if you compare with the original plane wave, the goal was to try to make an observer see just what that wave would have been, as if nothing had been there. As
So
if it had,
the observer is off at the right here, and what they see is continual uninterrupted waves,
Right.
as if that object weren't there at all.
right, or off at the left
that's
or the
cool.
right, anywhere. Yeah,
That's really cool.
yeah.
So you did this initially in the microwave wavelength. Why is that?
Because it's easier. This is really a conceptual thing, like I said. How do you make a material? And this, you can go down to Radio Shack or maybe a couple levels up, but it's very cheap, it's inexpensive, and you can make these things very, very quickly. And, I've got a short attention span and a lot of impatience, as do people in my group, and so we just wanted to see if it works. So these experiments we can do in a matter of hours, from basically concept to fabrication to result. And that's why we like working at microwave. It turns out also that 99.9% of the world's communication is done at microwave frequencies. So if you start asking if it's good for anything, you're exactly in the right regime to start asking that question.
Okay. And to go to a shorter wavelength to get towards visible light,
Right.
which is the thing that everybody cares about in invisibility cloaks, right?
Right.
You need smaller features. These copper icons need to be smaller.
Right. So there's problems, and I'll just back up and say not everyone wants to see or not see invisibility cloaks at optical, because that occupies a tiny fraction of the electromagnetic spectrum,
Yeah.
but it's the important one to us. So yes, light waves are about half a micron, and a micron is a millionth of a meter. So it's tiny. So if you wanted to scale this to optical, you would have to really scale these elements down to submicron sizes, nanometer size.
How do you know what shape to make those individual features? I notice in each of these materials they have a slightly different look
Right,
to them.
and that's basically the science behind this. We've learned how to create these shapes to do exactly what we want them to do. So we want them to have a certain type of electric and magnetic response, and we know if we, for example, make a circle with a cut, that will give us a magnetic response. We know if we change the shape just a slight bit, it'll have a certain electric response. And the combination of those things allows us to control refractive index and other properties that allow us to control light.
Which led, in fact, to the 2009 paper, which you called the next generation lens. You were able to use this refractive property to make the light focus.
That's right. That's right.
What was that experiment about?
So I think that was 2010, but in addition to making invisibility cloaks, which have a very specific audience, something much more common is a lens. And most lenses have aberrations, but there's certain types of lenses that have no aberration. One example is something called a Lumberg lens. A Lumberg lens takes light from infinity, and every ray can be focused perfectly to a point. And in addition, it's because the lens is a circle, it's basically a sphere. It's a ball. It works from any angle, so it's a wide-angle lens with no aberrations. And it's a well-known solution, but the problem is it's circular, and you can't put a planar detector on the other side. So you can't put a CCD or something. So they have limited use. And that experiment made use of the same technique that we did for the invisibility cloak to do what we'll call a coordinate transformation. We were able to flatten the side and figure out what sort of material we'd have to replace the original Lumberg lens with in order to get the same properties, but now with a flat side.
And how did that turn out?
It turned out great. We were able to demonstrate that we could get the properties of a Lumberg in this now metamaterial weird structure that was anisotropic and had all sorts of different properties.
Yeah. Let's take a little digression here to talk about a gentleman named Sir John Penry, who's considered the father of this idea. Tell us who he is.
Sir John Penry is a British physicist. He was a solid-state physicist who moved into photonics sometime in the 90s. And he influenced us because he started looking at these types of materials, metals, in different patterns. Mm-hmm. He actually was rediscovering something that had been known in the 40s and 50s, but he brought in a physicist's point of view and a more fundamental point of view that connected really well with the nanophotonics community. And in looking at his structures that were theory, he's a theorist, we decided to start demonstrating them. When I was in San Diego at the time, that's one of the first things I did. And at the time, it's interesting because no one cared about this. No one uses, at that time, metals optics because they were considered too lossy. So the work he was doing was very controversial. Mm-hmm. People either didn't understand it or didn't like it. So he's taken a lot of abuse and a lot of controversy. So we started doing experiments, and the only ones probably, and he introduced first wires, and he said that would have a certain interesting property. And then he introduced these structures, these rings, and he said these would have a magnetic response. Mm-hmm. And so I started trying to do experiments to verify those properties. And in the process of doing that, I came into contact with him, and we started working together, and we've been working together ever since.
Yeah. And he must be thrilled to see his idea
yes.
be a real object.
Yeah, it was fantastic. I mean, it was a surprising result that it generated so much attention. I mean, you use words like invisibility and cloaking and teleportation. All these things are out there,
right.
But somehow this was a little bit more real and really generated a lot of attention. And it's a very theoretical, interesting, beautiful type of mathematics that actually we can realize, and we could only realize it making artificial materials. Mm-hmm. You either couldn't, or it would be very difficult to make these same sorts of things using any kind of conventional materials.
Yeah. So far, we've been talking about electromagnetic spectrum, microwave headed towards light. But there are other ideas at work here. Last year, a member of your group had something about transferring wireless power over greater distances.
Right.
How does that work with metamaterials?
That was an interesting problem that we looked at in cooperation with a company called Mitsubishi, which most people know.
Heard of it, yeah.
They were interested in they came to us and said, can we use metamaterials for anything related to wireless power transfer? That's an important problem in society, and we'd like to take a look. And actually, they suggested the format of using something called the perfect lens. Going back to Sir John Penry, he predicted something called the perfect lens. If you have a material with a negative index of refraction, you can make something that looks just like a slab, like this, mm-hmm. and it will have, he predicted it would be able to act as function as a lens and beat the diffraction limit. So you could have resolution greater than any lens that exists. So Mitsubishi...
I have to sneak in a definition here. Negative index means the incident ray is bent exactly the opposite direction that you would have expected otherwise.
Right. Most people know the index of refraction of material is what tells you how much the light bends when it enters that material.
As through a glass of water.
Right.
Yeah.
And so for negative index material, it bends completely the other way.
Right.
It bends backwards, does a backflip.
Okay, sorry, I interrupted.
So no problem. And so the negative index lens, actually Mitsubishi came to us and said, if we had a source coil and a receiver coil, which is being used in a lot of wireless power transfer systems.
Implantable medical devices.
For example.
Uh-huh.
If you placed a perfect lens between them, could you enhance the efficiency? And efficiency is everything in power transfer.
Right.
And so we started looking at that with them, and it turns out you can. And it was a nice, probably one of the best uses and unintended uses of a technology that was just a pure physics concept not too long ago.
So wireless power transfer now is being used in some medical devices, but it's only over a very short range. What the metamaterial did was focus that energy more tightly so that you could go over a further distance?
Right, that's right, and give you more efficiency in transferring. What happens is if you have a coil, the field's from that fringe everywhere.
Yeah.
And so you have to be very close or you're left with nothing. So you need something like a lens, but until now there really was no lens that worked in that regime.
Yeah.
These are waves, they're considered waves, but they're kilometers long.
What is the medium for electricity transfer? How does that? I don't even know how that works.
Well, normally it's wires, right?
Yeah.
But your cell phone and your PDA and your laptop all work with microwaves
Right.
wirelessly.
Right.
So it's electromagnetic radiation. It's light, except we just can't see it.
Yeah.
But your laptop can see it.
Yeah.
And so it's communicating constantly. And now people are talking about using that same medium, that same venue to transfer power, which is much nicer than having lots of wires, and especially important for things like electric vehicle charging.
Yeah. I just want to remind our audience that they don't need to lurk in silence. They can email a question to you, live@duke.edu. They can tweet with the hashtag DukeLive, all one word, or they could post to the Duke University Facebook page. So we do have one question actually in over the transom so far. This one's getting a little ahead of ourselves, but let's take a time out and do it. Jack asked via email, suppose we're 10 or 20 years out now, this technology has moved from theoretical to practical. How might a terrorist use cloaking technology to their advantage?
So it's a good question. And again, I'd go back to the fact that the electromagnetic spectrum is huge. And we use a very small part of it, but we have detectors that are looking everywhere. There's the infrared, most people are familiar with that. There's terahertz, there's microwave, there's millimeter. And all of the things that a terrorist might want to hide are sometimes more easily seen at those other wavelengths. For example, if you hide something under your jacket, it's hidden to you,
Right.
but other wavelengths can see it.
Right.
And some of those wavelengths are now, our technology is actually being able to achieve cloaking at those wavelengths. So a terrorist might be able to sneak something in by cloaking it if he knows that a detector is looking at a certain wavelength.
Would a person with limited resources, I mean, you make these in our chip manufacturing facility, the Smith. That's a pretty sophisticated thing to make, isn't it?
This is not done in the Smith. This is done just in a light box and with materials you could get from Radio Shack.
Uh-oh.
And again, we're talking 10 to 20 years, right? Today's technology becomes tomorrow's commodity.
Yeah.
So, you know, the technology in an iPhone is ridiculous, but there's billions of them, or maybe hundreds of millions of them in the world. So, you know, when you think forward in the future, it's hard to project.
Yeah.
So you want to create the technology and then the counter technology.
Yeah. Needless to say, there has been military interest in this. I believe you have some DARPA money.
We had DARPA money initially, that's right, yeah.
And last year, pardon the pun, you had a paper that created a splash talking about hiding water waves with this same idea.
Right.
And a lot of the stories about that had a stealth submarine. Explain that for us a little bit.
So I should say that there's much, our group primarily does electromagnetics.
Right.
But the concept that is at work in cloaking and some of the other things that we've talked about is called transformation optics. And at Duke, we have Steve Kummer in our department, who's a faculty member, who has done a lot of work on acoustic waves, for example, in addition to electromagnetic, and also elastic waves. So these are waves that travel not in space as electromagnetic waves do, but in a medium.
On the beach.
On the beach.
Yeah.
Water, and fluids represent another type of phenomena. And an associate in our group named Yaroslav Urzhamov started looking at other types of physics to see how transformation optics could be used, always with the idea that these other types of phenomena interact with materials. So if you get more control over the materials, you can start to compensate or deal with other types of wave phenomena. So what he looked at was fluid flow, which is not a wave phenomena, but the equations can sometimes look similar.
Interesting.
And so he said, if we now look at what we could do with structured materials that control fluids, say porous materials, we could actually bend fluid lines around and effectively cloak an object from a fluid flow stream.
Such that a ship would have no wake.
Such that a ship would have no wake.
But my question about that at the time, David, was, wait a second, the density and salinity of the ocean changed from one minute to the next. How would you calibrate that thing to be effective in all situations?
So there's a very great difference between the inception of an idea and ultimately how it might be carried out. So I think what Yaroslav did was to demonstrate that the concept is a possibility. And even since that was published, a lot of people have come to us and said, well, look, here's this problem, there's that problem. And now we're starting to look at things like that. And Yaroslav's doing a fantastic job at addressing some of those concerns and changing the environment where you could actually use this. But you're absolutely right. There's limitations, and we are in this act of exploring all the limitations and what we can actually do.
Yeah. Obviously, it's worth pursuing, even though we didn't crack it the first time out.
Right.
I had the same thought about your prototypes here. I could see somebody looking at these and saying, "Oh, they're so large, they're so crude." But I'm remembering the first transistor was something bigger than a light bulb. So, and now I got 1 million of them in my phone. So,
Yeah.
I guess I'm not too worried about that. Another regime, heat. Just this week, a French team used a metamaterial to mask the heat coming off a processing chip.
Right.
Very cool. Tell us about that.
So I just saw it briefly. I just happened on it because the press release just came out this week. But again, it's this idea of if you can put materials with controlled properties, and we know how to do that, we know how to change the thermal conductivity. And this mathematical prescription that we worked out with John Penry, Sir John, can be really applied to anything. So here's another case where heat flow is simply another physical phenomena. It's something that flows, and as it flows through materials, different materials will either resist or allow heat to flow better or worse. So now you arrange those materials in a certain way given to you by this coordinate transformation mathematics, and it represents yet another physical phenomena that can be controlled just by putting the right pattern of materials.
And is that something that could end up being an improvement on the little heat sink vent thing that I've got on my processor?
Yes, definitely.
So you mask that hot chip and protect the rest of the device.
Like, again, these are just the inception of ideas, and people are looking at things including islands from tsunamis. And in principle, it's a possibility, but there's a lot of steps to go from here to there.
Yeah. I'm wondering also if Yaroslav's idea could be used to reduce drag on an aircraft.
Right, that's right. That's one of the things it would do. When you eliminate, when you improve the fluid flow, you basically mask or cloak in that case that type of resistance.
Yeah.
So maybe you could cut down turbulence, maybe all the things that would tend to retard your smooth passage.
Yeah. So in that corner of your whiteboard where you put the goofy out there things we'd love to know ideas, what's on that list at this point?
I tend to be really conservative.
Yeah.
And so a lot of this emerged from a path that was just completely rational and sensible. We never sat down to make an invisibility cloak. We were just following this, what can you do with materials?
Yeah.
And things start to fall out. But I think on the drawing board are a whole list of different types of phenomena. One of the more interesting, I don't, again, know if it's useful for anything, is cloaking matter waves. So, for example, imagine a bullet heading at you, which is a piece of mass. Could you somehow, we know quantum mechanically it's composed of waves. Could you divert that by having it somehow make a cloak for a bullet?
Wow.
It's not really a feasible idea at all, but people have shown at the quantum mechanical level with atoms and down at that very fundamental level that you can do things with matter waves.
Yeah.
At least the theory's out there, and people are actually trying to do the experiments.
Yeah, matter waves make my head hurt because I'm still thinking force equals mass times acceleration. That bullet has to go somewhere. If it's a Kevlar vest, I get a bruise and it dissipates through the vest. But you're talking about some quantum dissipation
Right,
of the energy?
some quantum, some quantum decoherence, deconstruction, reconstruction that would work just the same way of this. It's a wave phenomena. There's other things that make that you asked what's on the very, very tiny corner of the board.
I'm sorry.
So there you go. I mean, that's something that
totally out there.
and we write very small.
Yeah, okay, and then back to the electromagnetic regime where you are. You're working on smaller and smaller features to get to smaller and smaller wavelengths.
Right.
And in that case, then you would be using chipmaking.
That's right. And so we work with Nan Jokerst, who's another faculty member in ECE, to make very, very small structures that work for terahertz and infrared and visible wavelengths.
Yeah. Okay. So we're coming up on a half hour. Let me just wrap up by asking you again, in my own words, 10 to 20 years from now, put on your your Harry Potter cap and predict for us, where might we start to see these things? Where might the ordinary public? I mean, I imagine the military will have it first, but where else would it be, say, in a decade or 2 decades?
I think things are moving towards commercialization very quickly, so I think very soon you may see things in the communications realm. So you'll see not cloaks, but types of antennas that are really facilitated by metamaterials in things like satellite communication or
Cool.
cellular communication or things like that.
A cell phone that won't drop calls?
We'll drop calls maybe less.
Okay, great. Thank you very much, David. Appreciate you being with us today.
Thank you.
Enjoyed the conversation. Thanks.
Produced by Duke University. Online at duke.edu.